Okay, by popular request, let's do another session of how do you apply problem-solving techniques to think about something kind of larger and more complicated than you're used to. So here we've got two piecewise defined functions, and I was asking you to compose them. Find g of f of x or f of g of x. Well, and f of g of x. So I think a good technique to use here is to think about kind of what's similar about this and other problems that you know how to do, so that way you can zero in on what makes this uniquely difficult, what makes this different than things that you know how to do. And then you can try and focus your attention just on the things that are different. So let's get out a piece of paper. So let's first connect this to some stuff we know how to do. We know how to compose functions when they are not defined, in pieces. So let's just do that really quickly. Let's pretend we're going to take the third piece of f here, just this, and the second piece of g. And if I was going to find f of g of x, we know that's the same as f of g of x. And so g of x is the same as x squared. So that would be like the input to the f function. So I've replaced g of x with the equation that it is defined as. And then x squared becomes now the input to f. So the f function is pi to the x minus 2 minus 1, but we're plugging in x squared, we're plugging in x squared as the input to f. So this is x squared. So the final answer here would be pi to the x squared minus 2 minus 1. That would be f of g of x. Okay, so what makes this problem different than that? So what makes it different is that we don't know which ones to plug in where. We've got 3 pieces here, we've got 2 pieces there. If I told you plug in this piece of g to that piece of f, you could do it. Or if I said plug in this piece of g to that piece of f, you could do it. So what we really need to figure out is, how do you know which rules apply for each function? So let's go ahead and tinker a little bit. Let's just run some very simple experiments and start to notice things that might help us decide. So if I was going to try and graph this, for example, if I'm going to graph f of g of x, right away I could just choose some x values. What if x equals 2? And I'd think, all right, how do I decide which of the 2 rules applies? Well, it depends on the domain, the x value I choose. Is it in the domain for part 1 or part 2 of g's pieces? So it looks like whenever I choose an x value that's positive, I'm going to be using this second rule from g. So I can bracket this entire region here, and I know that g2 is going to apply to this entire region because we've got positive x values here, and I plug into the g function first, and positive x values in g always mean x squared. All right, so let's choose one and kind of see how it works out. Let's pretend I choose x equals 3. So I plug 3 in, I get 9 as the output, and now I notice that that actually doesn't fit any of the rules for f, because the third piece here only goes up to 5. So any values larger than 5 aren't defined inputs for the f function. So I know that actually this is outside the domain of f of g of x, because when I tried to plug x equals 3 in, I didn't get a defined output. All right, well, so let's try something smaller. Let's try something like 2. So if I plug in 2 to the g function, the output here is 4, and I see that that applies to rule 3 here. So you could plug that in and figure out what the value was and plot it. But remember what we're trying to figure out. All we're interested in is, how do you know which functions to plug into each other when we're trying to do the composition? So I know this entire region, for any x value, I'm going to be using the second part of g. What I've learned here is that for 2, I'm going to be plugging the second part of g into the third part of f because of the output of the second part of g. This output landed in the domain for the third part of f. Is that true? So now I'm thinking, is that true for all of the x values in this interval? Let's try another example. Let's try 1. So if I plug in x equals 1, again, I'm plugging it into the g function. I get an output of 1. And I'm noticing that that actually doesn't fall in the domain for the third part of f. because the third part of f, x has to be larger than 1. So that falls in the domain for the second part of f. So here it would be f2. So if I'm trying to think about the intervals where different rules get plugged into each other, what I've learned is that as long as x is larger than 1, in this entire interval, I'm going to be composing, let's see, g2 is going to be the input to f3. So I'm going to be plugging x squared into pi to the x minus 2 minus 1. And the reason I know that is because I saw what's the size of the output when I plug in an x value, and the size of the output ensures that I'm going to be plugging the result of x squared into that equation. So that's kind of the right way to think about this. And so you can continue to try and plug in individual points, but you could also step back and try and think, is there a shortcut? Is there a way where I don't have to plug in individual points? And what I'm realizing here is that we already know that any x value, any positive x value is going to get plugged into x squared. So all we really have to decide is the output from g, which of the f parts does it get plugged into? And that depends on how big the output from g is. And it'll tell us like which one of these is happening. So I already decided that if x is larger than 1, we're going to be plugging into f3. What about between 0 and 1? I already know that the output of x squared between 0 and 1 is also between 0 and 1. You can imagine, like let's do a little graph over here. Here's x squared. So if I plug in any input between 0 and 1, the output is also going to be between 0 and 1 because of the shape of that curve. So what that tells me is that when the input, when x is between 0 and 1, the output of this is also between 0 and 1, which means I've got to be using that middle part here. So in this region, it's going to be a different composition. It's going to be the second part of g, but it's going to be composed with the second part of f. So I can start making my piecewise defined function already. So if I'm defining f of g of x, we've got two intervals, the interval between 0 and 1 and the interval between 1 and, we actually don't know what. We know that 3 is not in the domain, but we didn't calculate yet kind of how far out can you get. So let's leave that part as a question mark for the moment. What are the rules that we use? Well, we said that in this interval, we're plugging g2 into f3. So g2 is x squared. We're plugging that into this one. And we already computed that sort of as the warm-up. So we would end up getting pi to the x squared minus 2 minus 1. All right, for this interval between 0 and 1, we'd be plugging x squared into f2. So here's the f function, 1 minus x, but remember we're plugging the output from g, so we're plugging x squared in as the x value. All right, let's keep going. For the last piece of this, I know that if I plug in a negative value for x, and remember I'm plugging it into the g function, because that's the inner function here for our composition. If x is negative, we're always going to be using the first part of g, because that's the domain where x is negative. So I'm always going to be using 2x. And now the same question. What is the output of 2x going to be for different inputs? Because that's what's going to tell us what piece of f we're going to send the output into. So if x is negative, 2x is also always going to be negative. So that means we know it's not going to be in this piece and it's not going to be in that piece. So for this entire interval, I know g1 is always going to get plugged into f1. So f1 of g1. And so now that lets us write our third piece. For the interval that's x less than 0, x less than 0, we're plugging 2x into this one. So 2 divided by 2x plus 2. It's probably a little silly to keep that there, so let's have those divide each other to make 1. So now we've got 1 over x plus 2. And then we have to ask ourselves, like, is that everything? It seems like this third rule applies for this entire interval, We've got this interval covered. We've got this interval covered up to whatever our maximum is. So that covers the entire domain of possible inputs for x. So I know I've only got 3 pieces here. And the reason I have 3 pieces instead of 2 pieces is because when x values are positive, the output of x squared can send us into 2 possible parts for f. And that's what that dotted line there is. All right, let's wrap it up by figuring out what's the largest thing this could be. So I sort of have to think backwards. I have to think, what's an x value where I plug in the x value here, and it gives me the largest possible number that's allowed for f. So the largest possible number allowed for f is 5. So what value could I plug in here that's going to give me 5? And the answer must be square root 5. If I plug in root 5 and I square it, that's going to give me an output of 5, which is just a little bit, it's sort of right on the end point of this interval. So what that tells me is that this mystery value is root 5, and that wouldn't be included in the domain because if I plugged in root 5, that actually doesn't give me a valid domain for this third part of f. But anything smaller, even a very little bit smaller. So the last thing we could do here is fill this in as x is between 1 and root 5, but not including root 5. So that would be a full solution to f of g of x. You can practice this same thing with the composition the other way, g of f of x. And when you compose them the other way, I haven't worked it out, so I don't know how many intervals there's going to be, but I think there's definitely more than 3. I think there's even more than 4. I think it might be 5. But you can, of course, check for yourself and find out. I hope that this was helpful. Wait, let's not end it. Let's sort of step backwards and say, okay, what were the thinking tools that we used to get to here? We thought, all right, to find a composition, I know I'm plugging some equation into another equation because we're interested in what happens when the output of one becomes the input of the other. What made this uniquely hard was we weren't sure which equation to plug into which other equation. And the way we solved it was by thinking about it like a piecewise defined function, because you know that particular inputs, if you look at what part includes that input in its domain, that's how you can figure out what part applies. So for different x values that are possible inputs to g, we could figure out which of the 2 g parts applies. But then the output of g is what's becoming the input of f, and that's what's telling us which part of f. So it's sort of like we have to match the ranges for the different parts of g to the domains for the different parts of f. So like that was probably not at all clear when you started this process, but hopefully by very clearly asking yourself, what's different? What do I really want to know? What parts of this tell me what I really want to know? By asking yourself very specific questions, you can reason your way to a pretty clear picture in your head, hopefully, of what's happening. Okay, now I really hope this was helpful. Thanks.